Good morning. Thank you so much for inviting and allowing me to share my story and experiences with amateur radio and robotics for you here today. My name is Carissa Ferguson, and I'm currently 17 years old and a high school senior from Norfolk Academy in Virginia. For me, it started a long time ago. At the age of 8, I acquired both my technician and general class amateur radio license. Pretty early age, to say the least. With robotics, on the other hand, I started much later in my life. I didn't really get into robotics until my sophomore year in high school. However, the more that I participated in robotics, the more that I realized that it wasn't actually that different from amateur radio. In fact, they're actually quite similar. It is in recognizing these similarities that we are then able to understand how both fields complement each other. But before we do all that, let's establish what amateur radio and robotics is first. For most of you here, you probably already know what amateur radio is. However, for those few, amateur radio is a regulated radio service which is often used for non-commercial purposes such as emergency communication, contesting, wireless experimentation, etc. Well, that's great. Like I said, most of you know that. But do you know what robotics is? Oftentimes, when someone says the word robotics, people often resort to images of Johnny Five or the Iron Giant. And if that's you, I honestly don't blame you. If you would have asked me a couple of years ago, I would have said or thought the exact same thing. However, I've come to learn that robotics is so much more than something out of a cheesy science fiction movie. In fact, it's much, much more than that. Robotics plays a huge role in our everyday life through automation, making life easier and efficient and more comfortable. In order to truly demonstrate what robotics is, I would like to take the time to walk you through one of the best robotics organizations out there, otherwise known as FIRST. Currently, FIRST is one of the largest STEM organizations worldwide with over 400 participants annually. They offer a total of 4 programs for students: FIRST LEGO League Junior, FIRST LEGO League, FIRST Tech Challenge, and FIRST Robotics Challenge. It is through these programs that FIRST hopes to help teach kids the science, engineering, and technology skills they need to be successful in the real world. Every year, FIRST presents us with a challenge. Depending on what program you do, the challenge itself tends to vary. Here, I'm only focusing on this year's FIRST Tech Challenge as an example. In this challenge, we were asked to design, build, and program a robot that is equipped to perform tasks such as retrieving and transferring of items, as well as navigating to and from certain parts of the field. As you can see, they're all very simple tasks. However, the real complexity comes from how we decide to actually go about them. Aside from a few rules here and there, we're basically given free rein to tackle these problems however we want. This allows for students to develop the problem-solving skills they need without impeding on any of their own creativity or ingenuity. After the challenge has been established, the team then breaks up into the following 3 groups: mechanical, electrical, and software. When building a robot, we always start by addressing the mechanical aspects first. Once we do that, we can then consider the robot's electrical components. Whereas the mechanical served as the actual skeleton of the robot, the electrical serves as the robot's central nervous system. This acts as a network in which relays messages and information from the microprocessor, or the brains of the operation, to all parts of the robot. Finally, it is up to the software team to actually provide the code or the intelligence of the robot to the microprocessor to perform each task. It isn't really about how these 3 groups work individually, but rather how they work together. The key to any good team is collaboration, and robotics isn't any different. As you can see here, all 3 groups are reliant on the other. Mechanical cannot exist without the electrical cannot exist without the software, and so forth. All 3 parts are needed to work together if they're ever going to make one whole. This emphasizes the importance of team effort and cooperation among groupmates. After we finish the robot, we can finally take it to compete with. For me, competition day is one of my favorite parts of FIRST. It's always fun to see your hard work finally pay off on the field, but it's even more fun to see all the different robots out there. By looking and interacting with them, you get a taste for newer, different ideas. You begin to think, oh, I never thought of doing it that way. Or maybe I should try doing this instead. At competitions, you're constantly evaluating and reevaluating your own robot's design so that the next time you can compete, it can be even better. This just goes to show how robotics teaches kids to never stop thinking, because improvements can always be made. Having now defined what amateur radio and robotics is and what they do, I can finally point out some of the technological similarities that I've found in both. For example, robotics, much like amateur radio, requires a communications link for command and control. In order to maintain a reliable communications channel, both fields must calculate a link budget analysis, taking into account the receive and transmitter gain, power, bandwidth, and distance. Furthermore, both robotics and amateur radio rely on the use of microprocessors to complete tasks. These microprocessors can control everything from basic relays, motor movement, frequency measurements, and analog to digital conversion. Because microprocessors cannot act on their own, additional circuitry is almost always required. Circuitry acts as the bridge between the analog and the digital world. And of course, because we don't live in a world where the Energizer Bunny beats his drum forever as in the commercials, we have to analyze our power due to our limited source of energy. For amateur radio, this can apply to emergency communications, summit operations, and camping. As for robotics, we face similar challenges due to the limits of size and weight constraints. Now I would like to walk you through a project that I created in which some of the commonalities as mentioned beforehand apply. The objective of this project was to take the automation of robotics and then apply it to amateur radio. I call this project the CIB sniffer. In essence, it is a device that passively listens to a communications bus and makes a decision based on input frequency. But let's touch upon what exactly CIB is. In order for any communication to occur, there needs to be a certain set of rules in which two or more devices agree upon and follow. These set of rules are known as protocols. Protocols are used to define how data is formatted and structured. For me, I ended up using Icom's Communication Interface, or CIB system, based on the equipment that I happen to have on hand. The CIB message system is capable of conducting a variety of commands. However, for this project, we'll be only focusing on the following three: messages 00, 03, and 05. The reason why we're looking at these three specifically is because they all focus on the transferring, reading, and writing of operating frequency data. Another thing to note about the CIB system is that it has a fixed frame variable length format. Here, each of the boxes represents a byte. The first 2 bytes, as indicated by the pair of FEs, represents the message preamble. Basically, the preamble signals to everyone to pay attention and that a message is about to be sent. The next 2 bytes are the receive and transmit addresses. The next regard the actual message number. And following that is the frequency data, or small FE. Lastly, the large FD represents the postamble, thus indicating the end of the message. However, in order to work, the CIB sniffer requires some user input. The user needs to define a variety of things, such as the serial baud rate, the address that they're interested in, and the output state, aka what to turn on and turn off as a function of frequency. So how does it work? To put it simply, the CIB sniffer reads in the message on the CIB bus. When it encounters a message with the correct address and frequency information, it parses out that information, compares it to its programming, and turns on the appropriate state. Well, that sounds simple enough, but as you can see, starting design can be a bit overwhelming to say the least. You've got data sheets for the microprocessor, data sheets for the LEDs, data sheets for the level controller, data sheets for the relays, just data sheets on top of other data sheets. You've got so much information piled one after the other, you can easily get lost. Early on, I found myself constantly asking, where do I begin? Well, after shifting through all the data sheets, I decided to come up with 2 different boards, one with relays and one without. I then turned to EagleCAD to come up with a rough draft of the circuit. Creating a schematic in EagleCAD requires the end user to select the electrical symbols of the desired parts. Once the part symbols are selected and positioned on the sheets, the user connects the symbol using wire, and the schematic is built. The next 2 slides describe the bill of materials of the parts required to build the 2 different prototypes. The bill of materials is a living document which will change until the design is finalized. Here's the one with relays. And this is the one without. We then start breadboarding our first prototype by hand. The prototype was needed for software and hardware development. Some of the issues encountered were wires breaking off, old solder joints, relay drivers loading down the microprocessor, etc., etc. Eventually, it came to the conclusion that trying to debug the software using this hand-built prototype was just not going to cut it. So we then turned to Plan B and created a much more simpler circuit for debugging the software. The finalized schematic was then placed into EagleCAD for both versions. The one on the left indicates the one with relays, and on the right is the one without. Once the schematic is finalized, we must design or lay out the PC board. A word of caution. When using PC board layout software, the user should always create their own footprints for components. A little lesson I had to learn the hard way. I relied on some library footprints that I found on the internet and ended up with a bunch of useless PC boards. The EagleCAD programmer takes the schematic and assigns a footprint for each symbol. These footprints are attached electrically by air wires. The next step is to place the footprints into final position on the PC board. The final step is then to replace the air wire with the PC board trace. This can be accomplished by either manual operation or outer router. I use the manual mode. Anyways, after we finish laying out the board, we eventually send the board off. Board cost is a function of turn time, or how fast you can get it back. But just remember, the longer you wait, the more anxious you get. For me, I was absolutely sweating with anticipation. I was constantly worried about when the board was going to get here. I kept second-guessing myself left and right, wondering if I forgot something or if I made some stupid mistakes. When the board finally gets here, we have to assemble it, and to me, this is the most fun part of all. After we piece everything together or populate the board, we're finally ready to test it. And success, the board works. The left is the one without relays, and the one is with. So what exactly can we use the CIV sniffer for? Well, I would like to share some situations and scenarios where the CIV sniffer can be applied. Essentially, the CIV sniffer can be used externally or embedded to control various frequent dependent peripherals. You may or may not relate to the specific example yourself, but hear me out for a minute. Let's say you turn on the radio on 20 meters and you adjust your bandpass filter accordingly. You're operating, all of a sudden you look at the DX cluster and you see that rare DX contact you need, the one you've been looking for on 15 meters. In the heat of the moment, you switch the radio over to 15 meters, you key that microphone or strike that key and bam, pop. You let the smoke out of the box. You forgot to change the bandpass filter settings. Eventually bypass that filter and you make that contact and you say to yourself, boy, that was one expensive contact. You could have saved yourself the cost of repair bill on that $300 to $800 filter if you just used $15 worth of parts. The same principle can also be applied to solid-state amplifier control. However, microprocessors can do more than just turn relays. They can also be used to drive both DC and stepper motors. Here's a picture where I helped my dad implement a large commercial tuner to have frequency presets that control the position of the capacitors and the inductor using only a microprocessor. Manufacturers such as Alpha and OM Powers are currently starting to implement or design radio equipment using microprocessors for band switching. This feature helps to protect sensitive electronics, but raises the price of the unit dramatically, about $1,000 to $2,000 for automation. Today, I hope I've shown you how amateur radio and robotics can help each other out. For me, robotics operation will not end on a small competition field in a high school gym. In some of the future roles I see robotics helping amateur radio is in remote station operations. As for amateur radio, on the other hand, I see it helping robotics by extending the communication between the robot and the user by adding additional RF power and new waveforms for communication. Even though amateur radio and robotics may share a few common technological similarities, their similarities go much deeper than that. The real comparison between the two comes from looking at them at a more humanistic approach. Both amateur radio and robotics share the same common goal: to prepare the world's future scientists and engineers. The stuff these students take from robotics and amateur radio are things that they will carry on for the rest of their academic and professional careers. For me, who is graduating this year, I wish to use my knowledge from both to pursue a dual degree in biomedical and electrical engineering. However, my story and path doesn't have to be yours. The study of amateur radio and robotics can lead to basically anywhere, where the only limit is our imagination. Thank you.
are you applying?
Oh, I'm applying to a variety of college right now. A lot of upstate colleges, Clarkson University, RIT, Rensselaer. I'm also applying to University of Michigan Ann Arbor and Georgia Tech and Virginia Tech as well.
Wow.
Yeah, so a lot of applications. Yes.
Carissa, in a typical robotics competition, how many schools are involved and how many students in each school?
Okay, so it depends on what level you do. For qualifying, typically it's 28 teams per competition, and then it will narrow down from there. And then it's very, very international, so it's like a global. Yes.
Usually it's a team. If you're all by yourself.
Oh, thank you. I appreciate that. No, but it really is a team effort. You really cannot rely on one person. It's too broad of a spectrum to cover by yourself and whatnot. Yes.
Carissa, that first of all was a wonderful presentation, and it's just terrific to have you here, especially among all these old people. I think it's just great. And I just have a question. I have a 14-year-old grandson who lives in Hong Kong.
Oh, wow.
And I am trying to interest him to getting his ham radio ticket. And there they still use all the British rules. But regardless of that, he's very interested in today's software and all the things that you're talking about. So what would you suggest to him? How would you suggest that he could integrate your interest in ham radio with his interest in software? Is there a trend there that young people would like to look at?
I'm not a software person myself.
It
so
looks like you are.
I'm not. Took a computer science course 1 year. Was not my strong suit, to say the least. But I'll get back to you on that. Give me some time to think about it. And I'll get
Okay,
back to
fair
you.
enough. Thank you.
Yes, yes.
So was the first program through your high school?
Yes. Yes. Anybody?
You could advise that student to apply the software to robotics.
And look up first.
Yeah. All right. Thank you.
Thank you.
Thank you.